And systems of equations are just groups of equations. And the idea of a system is that the solution, or I shouldn't say the solution, I should say a solution, because there can be more than one, to a system. You can have systems with 3 or 4 or 5 or 55,000 equations, but we are just going to focus on systems of 2 equations, so I'll just focus my energies there in this definition. So the solution to a system of 2 equations is an ordered pair so an X and a Y that satisfies both equations. So anytime you're solving a system, you're looking for a solution, or you're looking for something that's a solution to all of the equations in the system. Like I said, we're just going to focus on having 2 equations. So our solutions will be ordered pairs, so an X value and a Y value. And the best way to really think about these and get an idea of like how they behave is by looking at them. So we're going to look at the graphs. There's 3 different types of systems that we can end up with, so we kind of categorize them. So 3, I don't want to say categories. Yeah, I guess we will. Of systems. So the first one, let's do X plus Y equals 5 and 2X minus Y equals -2. So like I said, the easiest way to like see these things is to actually see them like on a graph. So we'll go ahead and graph each of these lines separately. So when you're graphing systems or solving systems by graphing, you're just graphing X plus Y equals 5 and then separately graphing 2X minus Y equals -2. And then after you've graphed each one separately, then you look at them to find your solution. So I think when your X's and Y's are on the same side, the easiest way to graph is to find the intercepts. You could always just fall back on using a table, right, where you pick a bunch of X values, plug it in, and find all the Y values. But if you have X plus Y equals 5, so we'll do that guy first. If your X value is 0, then this term just goes away, right? You have 0 plus Y, and so you get Y equals 5, which means we have a Y-intercept of 0, 5. And if your Y value is 0, then this term just goes away. And so you just have X equals 5. And so our X-intercept is 1, 2, 3, 4, 5. So that's just like an easy way to get 2 points. If it's a straight line, all you need is 2 points to draw it. So getting those intercepts is pretty easy when the X and the Y are on the same side, just to kind of like cover up one of them, and that gives you the other one. So we'll draw a straight line through these guys. So that's our first line, and then our second line, we'll go with green, is going to be this guy. And again, I'll just look at the intercept. So if Y is 0, then this term goes away because we have 2X minus 0. And what would X be? Yeah, -1. You would just divide both sides by 2. So if the x or if the y goes away, you have the equation 2x equals -2. Divide both sides by 2, you get x equals -1. And so we have a point here at -1, 0. Whoops. Exactly. There we go. And then if x, what's up?
Oh, no, sorry. I was just...
Do you see it?
I do. So when you put a 0 for
Uh-huh.
y, I just thought adding 0 to the other side would make it positive, but that's not.
Right, and like when you put the 0 in, it really just goes away because 2x minus 0 is just 2x, right? Subtracting 0 from anything doesn't do anything.
Should it be on -1, not negative?
Oh, I'm so sorry. Yeah, you're right. I miscounted there. Thank you. -1, there it is. And then if x is 0, then 2 times 0 is 0, so that term is just 0, and we get -y equals -2, so what's y?
2.
Just positive 2, good. So we have 0, 2, and then we'll draw a line through those 2 points. So what we have now is all the solutions to both of those equations. So every single point on that blue line is going to be a solution to the first equation, and every single point on the green line is going to be a solution to the second equation. So where would I find the solution to the system?
Would be at the intersect.
Yeah, because that's the only point that's on both lines. So it's the only point that is a solution to both. Very good. So this is my solution. So this we have one solution. One solution. And it is, in this case, 4, 1. Nope, 1, 4. And when we have a system like this where we have two lines that are different from one another and they intersect at a single point, we say the system is consistent. So when we say a system is consistent, it just means it has at least one solution. So has solutions. It doesn't tell us how many solutions it has, but it has at least one point satisfying both equations. And then this system is also independent, which means that we have two different lines. So we'll see this in a minute, but if a system is dependent, then graphing both equations, we just end up graphing the same line twice. Like we graph one of them and then graphing the other one is just right on top. So that would be a dependent system. So anytime you have two different lines, the system is independent. And if you have any solutions at all, the system is consistent. So tonight in your homework, you'll be classifying systems, and you'll select either consistent or inconsistent and either independent or dependent for all of your systems. So far, so good? Okay, so the second categorization is something like, what did I do? X plus y equals 5, and y equals 5 minus x. Oops.
Are those the same equations?
They are. So this one is pretty obvious, just looking at the equations, that they're the same, right? If you take the first one and you subtract x from both sides, you get the second one. So manipulating one gives you the other. And so if we were to graph these, well, the first one is actually the same as the first equation on our last example, right? I have intercepts at 5, 0, and 0, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so there's my first line.
So if you can tell, do you still have to graph it?
You don't have to, I mean, if you're asked to graph, you have to graph. But like graphing isn't how we're going to solve these. It's just the best way to get an idea of like what they look like, what each situation looks like. Yeah. So then if y is equal to 5 minus x, well, we could graph this using slope and y-intercept. So the y-intercept is 0, 5. 1, 2, 3, 4, 5. What's the slope of this line? Yeah, so that means that, remember, slope is just how y changes when you increase x by 1. So if my slope is -1, that means I can go from any point to the right one and then down one to get a second point. And so if we draw our line through those 2 points, we see that it is in fact, I'm trying not to do it right on top so we can see both, but it is in fact the same exact line. And so does this system have any solutions?
Infinite, right?
Yeah, there's an infinite number of them, right? Because every single point on that line is a solution, right? Because every point on the line is a solution to both the green and blue. So is it consistent or inconsistent? It's consistent, right? Remember, consistent just means it has some solution. So this system is consistent. And then is it dependent or independent? Yeah, it's dependent because we don't get two separate lines, right? We get the same line twice. So we call that dependent. And when you're asked to solve this and you get this situation, you just say that there's an infinite number of solutions or infinitely many solutions. We have to be a little bit careful about how we interpret that infinitely many solutions, because the last time we had infinitely many solutions, it meant that all real numbers were solutions, right? Like everything was a solution. But if you look at the graph, like we can see that every point isn't a solution, right? Only points on that line are solutions. So it's not like when we solved in a single variable and we got an infinite number of solutions and that meant you could pick anything and it would work. Because like this point right here isn't a solution to either of those equations, right? So when we say infinitely many solutions, the reason there's an infinite number of them is because that line has an infinite number of points on it, not because you can just pick anything you want and it'll work automatically. So when we have a dependent system, it just means that if you have a point that is a solution to one of the equations, it will also be a solution to the other one. So we have to be a little bit careful with that distinction. And that's why we always write infinitely many solutions as opposed to like all real numbers or anything like that. Okay, last situation. What do you guys think?
Can you go back real quick
Uh-huh.
to the first one?
Yeah.
Okay, thank you.
So we've had one solution, we've had infinitely many solutions. What do you think we're missing? No solution. Yes, that's exactly right. So let's look at f of x equals 2x minus 4 and g of x equals 2x plus 1. So we'll go ahead and graph these guys. So f of x first. Remember the y value is just the output. So this is the same as graphing y equals 2x minus 4. So I'm going to use slope and y-intercept because it's in slope-intercept form. So my y-intercept is 0, negative 4. 1, 2, 3, 4. It's right here. And then the slope is 2, which means that moving to the right 1 unit increases my y value by 2. So from that point, I'll move to the right 1 unit and go up 2 units. So there's my first line. And then we'll do this guy. So my y-intercept is 0, 1, which is right here. And again, my slope is 2, so that means that moving to the right 1 unit will increase my y value by 2 units, so that gets me right here. And again, you don't have to graph using intercepts or using the slope and y-intercept. You can always just make a table like we have been doing with graphing. Some of these tricks are just a little faster, but that doesn't mean you have to use them. Yes?
How many points lost you got?
You only need 2 for a straight line. So what can you tell me about these lines? They're parallel, right? Which means they never intersect. So if all the solutions to my first equation are on the blue line and all the solutions to my second equation are on the pink line, if those two lines never intersect, then there's no point that is a solution to both of them. And so that's when we have no solution. I feel like it gets worse every day. Okay. So we have no solution. So when we classify this system, is it going to be consistent or inconsistent?
Inconsistent.
Yeah, it's inconsistent because it does not have any solutions. And then it's really redundant to say, and normally we don't even say it, but it's also independent. It's redundant because if two lines never intersect, they certainly can't be the same line, right? So if we say it's inconsistent, we're already saying it's not the same line. But in your homework, they make you choose one for every single problem. So all inconsistent systems are also independent. There is no such thing as an inconsistent dependent system. Okay, so that's our 3 different situations that we can get into. And graphing is really nice because you can see what it looks like and where those solutions really are. But actually solving these systems using graphing is not very efficient. One, because drawing straight lines is like perfectly straight lines isn't always that easy. And secondly, because all our solutions aren't necessarily going to be like nice integer points, right? If you have a decimal or a fraction as a solution, it's really hard to pinpoint like exactly what that point right there is, right? As far as the exact decimal or exact fraction. And so we need an algebraic way of solving these guys. And we're going to focus on the method called substitution. So solving by substitution. There's another method called elimination that we'll talk briefly about tomorrow. But for our purposes and when working with functions, usually substitution is the most practical way to go. So we're going to focus on that. And it's really easier to sort of show by example than to try to like write a big list of steps. So we'll just do a bunch of examples here. So let's say we have the system, let's do x plus y equals 4 and x equals y plus 1. So I want both of these to be true. So if I assume that they're both true, then that second equation tells me that x and y plus 1 have the same value no matter what, right? That's what an equal sign means, which means anywhere I see an x, I can put a y plus 1, and I haven't changed anything because they have the same value. So what I'm going to do is I'm going to take my first equation, and instead of writing an x, I'm going to write a y plus 1. So all I'm doing is taking the information from the second equation and using it to substitute for that x in the first equation. So instead of x, I've got y plus 1, and then plus y equals 4. Everybody cool with that? And now I have an equation that only has one variable in it, which is nice because we know how to solve those. So we'll combine like terms. We get 2y plus 1 equals 4. So 2y equals 3, and y equals 3/2. And we're not quite done because we have to get an ordered pair. So we need x as well. So we're going to take this guy back over here and say, okay, now I know what y is, and I'll get x if I add 1 to it. Yes?
How did you get 2y?
Y plus y.
Oh, okay. I thought you were multiplying, so I was confused.
Yeah, so the only thing being distributed here is a 1. Right? And so that just drops my parentheses, essentially. And so adding gives me 5/2. So my solution is 5/2, 3/2. So the order that I used my equations in doesn't matter. So like the reason that I substituted the second one into the first is because the second one is solved for x. And so it's easy for me to say, okay, anywhere I see an x, I'll put a y plus 1. It doesn't matter which is which, though. So if the first equation had been solved for x, I could have substituted it into the second. And it also doesn't matter which variable you substitute. If one of your equations is solved for y, you can substitute for y in your other equation. So you have some choices as far as like the order you do it in. But the general idea is that you want one of the equations solved for one of the variables. You'll use that to substitute into the other equation. So it's not always quite as nice as this when you're first given it. So you don't always get something like this where one of your variables is already solved for. So often that's the first step, is to just get one of the variables alone in one of the equations. So let's look at one like that. So let's solve 2x plus y equals 6, and 3x plus 4y equals 4. So my first job here is to substitute, or to solve one of the equations for one of the variables. Anybody have any ideas which one I might... Yeah, which variable you want to solve for? Y. Yeah, so everybody kind of sees why that's the most maybe efficient choice. It's not like the only right choice, but when you have a coefficient of 1, so no number in front of one of the variables, it's usually the easiest one to solve for. Because if I, for instance, if I solved the second equation for y, I would have to subtract 3x and then divide both sides by 4, and then all of a sudden I have a bunch of fractions that I have to deal with. So if one of your variables doesn't have a number in front of it, so it has a coefficient of 1, then you can solve for it without getting a bunch of messy fractions, which is nice because it just doesn't open up as much room for error. So we'll go ahead and take that first equation and write it as y equals 6 minus 2x. And then we're going to substitute that into the second equation for y. So we have 3x plus 4 times 6 minus 2x equals 4. Always make sure to put whatever you're substituting in for your y should be put in parentheses, or x, whatever you're substituting for anything. So now we can distribute. So we have 3x plus 24 minus 8x equals 4. Combine like terms. Subtract 24 from both sides. And then divide both sides by -5, and we get x equals 4. So then I'm going to take that guy back up here to get y. So y equals 6 minus 2 times 4. And that gives me y equals -2. In reality, when you plug, like once you solve for one of your variables, you can plug it back into either one of the equations. Like I could plug it back in here and solve for y as well. But since I already got y alone over here, it's probably the simplest thing to do to just go back into that equation. So it's not that you have to use that one, but it's usually the most efficient way to go. Okay, you guys ready to try one? Okay. Let's solve x minus 2y equals 3 and 4x minus plus 2y equals 7. Equation for x. So we had x equals 3 plus 2y, or 2y plus 3, doesn't matter the order. And so then we have 4 times 3 plus 2y plus 2y equals 7. So 12 plus 8y plus 2y equals 7. And I think that ends up giving us 10y equals -5, yeah? After a couple steps, and then y equals -1/2. And so then we'll substitute that back up here. So we have x equals 3 plus 2 times -1/2. Gives us x equals 3 minus 1, which is 2. Look good? Okay, so our solution is 2 -1/2. Oh, and one thing I should mention, on the online homework, like, I almost always use x's and y's, but like our textbook likes to use p's and q's and s's and t's and all sorts of other variables. So if you come across one that uses different variables, when you write the ordered pair, it's always in alphabetical order. So if your variables are a and b, then it would be a comma b. So that's just the easy way to remember, like once you solve for them, like which order to actually put them in your point. So let's look at, I didn't delete this one. I'll do it again. Let's do x minus 2y equals 3 and 2y equals, no, not 2y. 6y equals 3x plus 9. Okay, go ahead and solve that one. No, that's the answer. Yep. If you did it right and you try it again, you should get the same thing. I mean, you always can try again, but hopefully you'll get the same thing. Okay, so if we solve for x, this first equation is in fact exactly the same as in the last example. And so we're going to plug 3 plus 2y in. So we end up with 6y equals 9 plus 6y plus 9, which gives me 6y plus 18. What do I get on the left side if I subtract 6y from both sides? Just 0, right? So we get 0 equals 18, which tells me what? That there's no solution. So it's just like when we were solving equations with one variable. If you end up in a place where you have a number is equal to another number, that just means no solution. And if we had ended up with like 18 equals 18, that's always true, right? So that would have been when we have our dependent system, so when we had an infinite number of solutions. So algebraically, we end up with that same, it looks exactly the same as when we're solving equations in a single variable and we end up with an infinite number of solutions or no solution. So we have no solution. And then one more that we want to look at that looks a little bit different but is in fact really the same thing is, it's just a different way of asking the question. So if I say find the point where the graphs of f of x equals negative 3x plus 5 and g of x equals 4x minus 5 intersect. So this is just another way of asking you to solve a system. So asking where two graphs intersect is the same as asking what's the solution to the system. So remember that when we have something in function notation, that this is identical to y equals negative 3x plus 5. And the graph of this one is given by y equals 4x minus 5. So really, when they're in function notation, all we have to do is set the outputs equal to each other, right? F of x is equal to some expression, g of x is equal to some expression. If we want the outputs to be equal, we just have to set those expressions equal to each other. So in reality, what we're doing is we're saying, okay, y is equal to negative 3x plus 5, so we can take negative 3x plus 5 and substitute it for this y. So in reality, we're just doing substitution again, but this one's even a little simpler because all you really have to do is set the two equal to one another. So we say the output of f of x, which is negative 3x plus 5, has to be equal to the output of g of x, which is 4x minus 5. So we're just setting the two functions equal to one another. So these ones actually end up being a little simpler even because you don't have to like solve for one of the variables because they're both already solved for y because they're in function notation. So then we'll subtract 4x. And subtract 5 from both sides. And then divide both sides by negative 7. So once you have your x value, to get your y value, you can just plug it into either one of the functions. So I'll evaluate f of 10/7 plus 5. It's not very pretty, but negative 30 over 7 plus 5 is 5/7.
You can plug that into either equation.
Yeah, and one thing that's kind of cool is like if this was a test or something, you could plug it into both, and if you don't get the same thing, then you know you made a mistake over here. So it's kind of nice to be able to know that you did something right, like before you hand a test in. So if we had done G of 10/7, so we'd get 4 times 10/7 minus 5, which is 40/7 minus 5. And 5 is 35/7, right? So 40 minus 35 is 5. So you get 5/7 both ways. And if you get the same output for both, that tells you got the right x. So your point of intersection is 10/7, 5/7. Questions?
Do you have to put independent or dependent on questions like these?
No. You only have to classify them if you're asked to classify them. Trying to think when I've ever even... I mean, I've used the words dependent and independent and consistent and inconsistent, but not...
Not as much as you think so.
Yeah, not until, like, way later.